Talk about aromatic compounds. Aromatic compounds have some pretty unique properties. The most, I guess, commonly known one, or the poster child of all aromatic compounds, is benzene. See if I can just draw benzene there real quick. So that's an example of one. Let's think about things that we can name, or things that we could say about aromatic compounds. Well, in every aromatic compounds, all carbon-carbon bonds are the same length. That's kind of helpful. Not really, but some things that we can imply about this. This is just the effect. But let's examine the cause of this. Well, the reason why this is the case is because it's a conjugated molecule. Conjugated, which I hope you can tell just by looking at it that that's conjugated. And if something is conjugated, what that means is that we have really effective overlap of p orbitals. Overlapping p orbitals doing their thing. I've already made videos explaining what a conjugated molecule is. And it really kind of connects to this, is that all carbons in a benzene or in an aromatic compound are sp2 with p orbitals. Why? Because they're conjugated. This is all kind of connected to the concept of what makes something really well at being conjugated. So another thing that we could imply, or things that we can say about this, is if it's conjugated, well, this isn't really so much connected to the concept of conjugation, but whenever we're talking about resonance structures, remember that a resonance structure, the major resonance structure, is what determines the geometry of your molecule. And so this is all carbon atoms are sp2 with p orbitals. Then one of the things that we can say is if they are all with sp2 and p orbitals, that means that the whole molecule is going to be planar. Because remember, if you're sp2, you're flat, you're in the plane. And that's really the only thing that I think is important about this. Let's talk about just real briefly, though, on the whole nomenclature issue. Nomenclature of aromatic compounds. And it's kind of confusing. It's kind of unusual, the way that it's put together. But there is, when you have substituted aromatic compounds, and then when there's substituted, and then when the compound itself is a substitution. So I'm going to say as a substituent. Yeah, that's not the cleanest thing ever. So let's go ahead. I don't know why I've waited so long to switch colors, but do this in colors here. So there's, whenever you have a, for example, say a monosubstituted compound, whatever it is, first thing you do is you just name the substituent. Just name the substituent, and two, add the words plus the words benzene. So I guess I'd try to give you an example of this. Here's a benzene aromatic compound with a nitro group, whatever. So what am I going to call this? Well, this is a nitrobenzene. Nitrobenzene. And I'm going to go ahead and circle that whole thing because this is really getting crowded. I should probably have done this on 2 pages, but that's one of the things. And then when it's a di-substituted aromatic compound, and again, not always benzene, but usually tends to be the case. There's some terms that we need to define, but really you'll just learn it by doing over and over and over again. There is a ortho, there is meta, and then there is para. So ortho is just where it's at the 1 and 2 carbons. Meta is where it's at, as you would have guessed it, we're going in chronological order, 1 and 3. And para is at 1 and 4. And when we get into the next chapter, these will make a lot more sense. But this is where, so I guess to draw examples of each of these, if I can fit them, I don't know if I'll be able to. So there's your benzene ring. Substituents at 1 and 2. I can think you can imagine that this would be 1 and 3. This would be a substituent at 1 and 4 on opposite ends. And these each have different reactivity and different reasons why we would have those. We'll go into that in a later video. The other thing that we could say, though, about substituted is that there is always polysubstituted ones. And for a polysubstituted aromatic compound, there's really 3 things that you're going to do. And I'm really getting messy, I know. But the first thing you're going to have is you're going to have the number the lowest, and you're going to alphabetize it. I'll explain what this means later. Alphabetize it, and then you're going to name as a benzene or an aromatic derivative of a common root. And I'll just explain. I'll do it. I'm running out of room here, but I'll explain this whole poly thing with the whole common root things later. But the last thing that I wanted to say is whenever something is a aromatic compound that exists as a substituent, there is a phenyl, not the same as phenol, which we'll talk about later. Phenol is a common root, but a phenyl is just a benzene ring as a substituent. So if you have something like this that's attached to, I don't know, say the rest of your molecule, we say that's a phenyl group. The other type of substituents that you can have is a benzyl substituent. Well, what is a benzyl substituent? That's where you have I guess the best way would be to just draw an example here. So you have, of course, a 6-membered ring that is a benzene group. It's aromatic. And there's a CH2 branching off of it, and then the rest of the molecule between it. This is just directly attached to the rest. There's a CH2 group kind of connecting those 2 groups there. And then the last thing that I have, and I won't even be able to give an example of it, but it's anything else really. We call it an aryl group. It means that it was derived. It is a benzene derivative. I can't even finish writing that out. It's a benzene derivative. So anything that has essentially a benzene ring in it that is not either one of these, we just go ahead and broadly put that under the category of saying that it's an aryl group. Okay, so now I want to talk about common roots because I didn't have enough room in that last little diagram. But let's talk about some common roots. So common roots for these type of things, there's really just 3 main ones that I think are important to know. Well, that the book gives. I'm not an organic chemist really. There's toluene. There's phenol, and then there's aniline. What do each of these look like? Well, a toluene is where you just have a benzene ring with a methyl group attached to it. A phenol group is, I feel like it's so commonly used, I feel like you should know this already, but in case you don't, there's an OH attached to our benzene ring. That's a horrible drawing, I know. But with an aniline is NH2 group, an amide. Not an amide, yeah, an amide group. Aniline has an NH2 group attached to it. So these are the common roots that you're going to use when you have a polysubstituted, or not necessarily just a polysubstituted, but whenever you have a polysubstituent. And these are also common names for these compounds. For example, if I said phenol, you knew that I was talking about just phenol. Okay, cool. So the next thing that we're going to go over is whether or not, and this is all that the chapter really focuses on, is whether or not a compound is aromatic or anti-aromatic or not aromatic at all. And I've already made a video, I think, on Huckel's rule, but let's just talk about things that make a compound aromatic. We kind of talked about this earlier, but let's just kind of go into the details of each of these. So if a molecule is aromatic, it has overlapping p orbitals to delocalize electron density. This forms conjugated pi bonds, or just, yeah, it's a conjugated pi bonds can be formed from this. I'll do the next one in magenta. It must be a planar molecule. It must be flat. So if it's planar and you have overlapping p orbitals, then that probably means that we're going to be sp2. I don't know why I say it like that. sp2 hybridized. And in part of that sp2 hybridized, we have p orbitals. Again, I just want to drive home that they delocalize electron density. The p orbitals. I think this is like the third time I've written this about the p orbitals, but this is a concept that you can't miss. This p orbitals will delocalize electron density. Okay, so the overlapping p orbitals must be planar. It must be completely conjugated. You can't have any type of spacing between the two. Conjugated and cyclic. What I mean by that is that you can't have an open end. So, for example, that is not an aromatic compound, whereas something that is completely conjugated and cyclic would be, even though that's conjugated, completely conjugated and cyclic. And the last thing is the 4n plus 2 rule, and I have a video on that for later parts of this course. So that's kind of I feel like I just repeated myself 4 times when I was doing this, but so what the hell does this mean? Well, what the heterocycle rule is, if you have a heteroatom that is not part of a double bond, count 1 lone pair towards the 4n plus 2 rule. So let's do some examples to kind of, I guess, distinguish between the two. When we had previously talked about in the last slide that when you have a molecule that is aromatic, it's got to be sp2 hybridized with a p orbital. So if something can have that, it's going to have that. And the two examples that I'm going to compare is going to be comparing pyridine with pyrrole. Hope I'm spelling these two right. I'm really bad at doing that. So let's just draw the structure of pyridine, and this is nothing new. You are familiarized with that. We've been going over this a lot in the last couple of chapters. There. It's kind of hard to draw with this pen, especially lone pairs. And then let's compare that with pyrrole. So pyrrole is kind of looks like this. There's a nitrogen group there. Lone pair there, lone pair there, dot, dot. And then there's an attachment to that. So for pyridine, the heterocycle is if you have a heteroatom that is not part of a double bond, count 1 lone pair towards the n plus 1 rule. So how many pi electrons am I going to find in pyridine? Well, there's 2, 4, and 6. So I have 6 for pyridine because that makes it way more stable. This in group here, this nitro group here, this is going to have its, I'm just going to draw it like kind of out like this. It's going to have his lone pair in an sp2 hybridized orbital. That lone pair exists in that, which just makes sense because that is a lot more reactive. You use pyridine for a lot of deprotonation reactions when we're doing the whole alcohols, ethers, and epoxide chapters. Now let's compare that though to pyrrole. So is pyrrole part of a double bond in this molecule? Well, no, it's not part of a double bond, right? So I'm going to count 1 lone pair towards the 4n plus 2 rule. 2, 4, 6, right? So if this has 6 pi electrons, and remember pi is, what is a pi bond? Well, overlapping p orbitals, right? That means that in this nitrogen atom here, even though it's got all these, trying to clarify here, even though it's got these things all bound to it, that pi bond exists in a p orbital. P orbital. And so that pi bond is going to be a part of that aromatic ring system. This pi bond is not going to be anywhere near as reactive as the pyridine, which is probably why we don't really use pyrrole, at least not for the same type of reactions that you would use for pyridine.